Welcome to lesson 4, inverse of a relation, f to the minus 1 of x. So when we talk about the inverse of a function, we have these general rules here. If f is a function with a domain A and range B, the inverse function, if it exists, is denoted by f to the minus 1 and has domain B and range A. F to the minus 1 maps y to x if and only if f maps x to y. So for example, it's a really simple switch in this situation. If you have the coordinate 3, 5, the reciprocal becomes 5, 3. Now, we've been working with reflections for the past week or so, and this one is a reflection as well, but it's across the line y equals x. You can see there we have that dotted line y equals f in these two graphs, y equals x in these two graphs. You can see here that we have this dotted line y equals x in these two graphs. On this one it's orange, this one it's green. Now, you have your function f of x, and it's reflected over that y equals x line to give you f to the minus 1 of x. The same thing here in this example, we have our original line y equals 2x plus 3, and it's reflected over that y equals x line, and the new equation for the line becomes y is equal to x minus 3 over 2, and we'll talk about how you come up with that equation a little bit later in the lesson. Just because we can switch the coordinates does not necessarily make the inverse function a function. So we have two tests that we can apply to our graphs once they're drawn to see if the function of the inverse exists. So it's called the horizontal line test, and it's very, very simple. All we do is draw a horizontal line through our original graph, and if at any point it only goes through the graph at one point, then we can say that the inverse exists. If you take your graph and you draw the horizontal line and it hits 2 points on your original graph, then we can say that no inverse exists because it's not a function. Now, you can also do this with a vertical line test when you draw your reciprocal graph. So if you aren't sure and you draw your reciprocal and the same thing, if it hits 2 points on your line, then we would say that the inverse does not exist. So we have this example. You have the equation f to the x is equal to 1/4 x minus 5. It's a vertical stretch in the y's of 1/4 and a shift 5 down. Now, all you do is write out the coordinates of f of x, and then to get your coordinates of your f to the minus 1x, it's very simple. You just switch them around so you can see your x becomes your y and your y becomes your x. And once you've done that, you can graph your new graph, which is here, f to the minus 1 of x. So we've done that. Now, the equation of f to the minus 1 of x is 4x plus 5 equals y, or 4x plus 20 equals y. And this is how you do that. Very simply, we have our original function here, y equals 1/4 x minus 5. All we're going to do is swap the x and y, and then solve for y to make it back into that y format. How we determine the equation of this f to minus 1 x line or graph that I'll talk about in just a little bit, but the basic thing that you do is you write out your original equation, you switch the x and y, and then you solve it back into that y format. So to get to this, we would add 5 to both sides, x plus 5, and then multiply both sides by 4. So that's why we have 4 times x plus 5 equals y. And if you graph this line, you would see that that is true, these two lines. Because we're working with straight lines here, there's not too much variability in the domain and range, but in a different shaped graph, you would see how these coordinates would switch. So all of our domain and range in both graphs is negative infinity to positive infinity, or x and y exist as our elements of real numbers. The second example we have here, we have a different shaped graph than we did before. It's just a plotted line. So Here we can apply the horizontal line test and draw a line straight through. And we can see that the horizontal line will hit at this point and this point. So that's a pretty good indication that the reciprocal is not in fact a function, but we can still graph it and see what the results are. So I've written down the original coordinates for this graph here, and then the new coordinates for this graph here. So you can see that it's just shifted its position by swapping the x's and the y's. Now, just like we did on the original graph, the horizontal line test, we can apply the vertical line test, and it would also fail here, proving that this is not in fact a function. But we can still pull some information and data from this graph. If you look on your next page of notes, we have some questions regarding the graphs here. So the first one is indicate the domain and range of the two functions. Now notice what happens. The domain becomes the range of f to minus 1x, or the inverse function, and the range becomes the domain. They swap places. I like drawing it out in this little table format because it's really clear what the changes have to be. And you can see that on the graph. In our original graph, we have -6 to +6, and that becomes our range in the inverse graph, so -6 to +6. And the same goes for the range and domain in the inverse. Now, the other thing that you've been asked to do is to determine the coordinates of the intercepts. So on the original graph, our x-intercept is here, -6 and 0. And our y-intercept is here, 0, 4. Notice how those things change in the new graph. We have our x-intercept at 4, 0, and our y-intercept at 0, -6. So there's a little bit of a switch in the coordinates there, and you should just be conscious of that when you're working. Another task that you might have to complete in this section is determining the equation of a reciprocal. So if we start with this original formula, given f of x is equal to 3x plus 6, evaluate f to the -1 of 2. And we need to first determine what the equation for the inverse relation is. And to do that, there's two different methods. You can either work by moving the letters around first, or you can work by inserting the value in y and solving for x. Whichever one you're more comfortable with is perfectly fine. I prefer method 1, but both are valid and correct. So in method 1, we have our original f of x is equal to 3x plus 6. We replace that f of x with y. And in this step here, all we're doing is switching the place of the x and y. Think of it like you're flipping your graph. Your x and y coordinates are just switching places. Now we're going to solve for back to y, but we need to move everything away from it. So we have plus 6 on this side. We're going to subtract 6 to move it to the left-hand side of the equal sign. And then we have 3 times y here. We'll just divide both sides by 3 to give us x minus 6 over 3 equals y. And that's the equation of our inverse function. Now, once we have this, we can take that value that was asked in the original question, f to the -1 if x equals 2, and just plug in a 2 wherever there's an x. So you get 2 minus 6 over 3, or -4 over 3. In method 2, you're doing the same amount of work. You're just inserting numbers instead of using the letters. So whichever way is more convenient for you, please do that one. It's the same amount of work, it's just a different method. So y equals 3x plus 6. You just plug in that 2 into the y value, and then the work becomes the same. 2, subtract 6 from both sides, divide both sides by 3, and you get the same answer at the end, -4/3. Another method that we can do to make sure that the inverse shown is a function is to restrict the domain on the original graph. So what we do is create a restriction of the domain f of x so that the inverse f to the -1x becomes a function. So if we have this original graph, f of x is equal to x squared minus 2. Here's a, b, and c. So step 1, graph the function. Is the inverse a function? So we graph our parabola and we shift it down 2. And we draw our horizontal line test. Now, it doesn't matter where you draw the horizontal line, as long as if the graph has a point where it could cut through 2 points, you put it in that area. So of course, because it's a parabola, no matter where you put it, the horizontal line test is going to fail. That tells us the inverse f of x is not a function. In part B, we can still graph the function as though it exists using the same simple rules that we used before. You're just switching x and y coordinates. So you can see here the vertex of our parabola is at 0, -2. It now switches to -2, 0, and then just carries on from there. So we've got this f to the -1x function available. However, if we do the vertical line test on this parabola, we're also going to see that it fails that test. So we would say that the inverse of this function is not 1. And then we can use this technique of restricting the domain to make sure that the inverse of a function passes that horizontal and vertical line test. So one possibility is to restrict the domain of f of x so that the resulting graph is only 1/2 of the parabola. Since the equation of the axis of symmetry is x = 0, we can restrict the domain right here. So basically, you're just looking for where it cuts the graph in half. So in this situation, we said x is greater than or equal to 0, and x is an element of the reals. So we're saying that all x values must be greater than 0, and it creates that graph there. Now, when we graph the inverse, just using this very simple point again, 0, -2, we just flip the x and y values, and it creates this nice half parabola shape. Now, if you did the horizontal line test on the black line, it would give you a pass as well. It would also pass on the vertical test. I should note that you could also have x is less than or equal to 0 as your new domain, and then it would be just this half of the graph placed there, and then this half of the graph would be placed for the inverse. Both of those will give you an appropriate result by restricting the domain to create an inverse function that exists. Beyond this, you have 2 practice questions related to the examples that I gave in the lesson, and you can complete those for class.